Welcome to Algebra 2. We've got section 4.4 today, factoring polynomials. Now, for our introduction, again, like we do on these videos, what I would do is pause the video and see if you can't make sense of this on your own. You know, give a couple minutes of thought on it, kind of read through the problem, see what you can come up with, and I'll check back with you in a few seconds. All right, hopefully we've had a chance to look at each function's graph and the function itself to see the x-intercepts and write the function out in fully factored form. So for this first function, x squared minus x minus 2, we can see from the graph that the x-intercepts are -1 and 2. Now realize that that's where this function has a height of 0. So we can kind of work backwards from our solving processes that we've used. In chapter 3, I think it was, when we solved quadratic functions, that zero product property. So we've got two factors. Since this is an x squared polynomial, we can see our two x-intercepts there. One at -1, well, that came from a factor of x plus 1. The other solution, the other 0, came when x equaled 2, so that comes from a factor of x minus 2. So those two places are where the function equals 0. So to represent the entire graph, we could say f of x equals the product of those two factors. So by working through the zeros, we arrive at the factors of that function, and we can express that function unfoiled. Now, obviously, if you were told to fully factor this, I hope you'd be able to do that on your own. But it's important to make the connections between the zeros, the factors, and the function itself. So let's try number 2. Here we've got a 0 at x equals -1, a 0 at x equals 0, and a 0 at x equals 3. So now we have three factors, x plus 1, x minus 0, and x minus 3. And those are the three places where our zero product property holds. So here is the fully factored function. But we can clean it up, right? X minus 0 is really just x, and then x plus 1, x minus 3. And again, we're looking for patterns and things here. Why does it make sense? Well, it makes sense because using the x-intercepts allows us to use the zero product property. That's kind of the connective tissue there. All right, for number 3, we've got -2, -1, 0, and 1. So those solutions, those zeros, would come from factors of x plus 2, x plus 1, x minus 0, and x minus 1. And if we clean that up, we get the factored polynomial x times x plus 2 times x plus 1 times x minus 1. And I hope that we're making the connection that, hey, this second degree polynomial, this quadratic, had two zeros, so it had two factors. This third degree polynomial had 3 zeros, so it can be written as having 3 factors. The fourth degree polynomial had 4 zeros, so we wrote that with 4 factors. That definitely is a pattern that we'll discuss in the second half of this chapter. All right, our key concepts today, we're really just building off the idea of factoring quadratic functions. So we had concepts like the greatest common factor, right, undistributing. The difference of squares, that was a nice little shortcut if we had two perfect squares with subtraction in the middle. And we also have our trinomial factoring techniques. Now we can combine these and also add in some other techniques to factor polynomials of higher degrees as well, and these are very useful because, again, the zeros are important points on the graphs, and if we can factor them, then we can find the zeros very easily. You'll see the term, or the phrase, factored completely. That just means that we've factored it to a point where we cannot factor it further with real numbers. So if we got to a factor that was like x squared plus 4, we can't factor that any further because it's not a difference of squares, it's a sum of squares, so we wouldn't proceed to factor that further. So we will be combining a lot of these techniques that we see up above. We just need to know it's factored completely. We need to know when to stop. All right, and just kind of a clarifying piece here at the bottom, a polynomial has a factor of x minus some number if and only if plugging that number into the function equals 0. And again, the reason this is so, plugging it into the function, remember our remainder theorem that we talked about earlier, if there's no remainder, it divides it cleanly, and that's the definition of what a factor is. All right, so what are the techniques we're going to be building on, or adding into our arsenal, I guess you could say? A sum or difference of perfect cubes. If I have my polynomial is two terms added or subtracted that are perfect cubes, then that equals the first, the cube root of the first thing, and then the same sign. So if this were a cubed plus b cubed, I would have a factor of a plus b. And then the second factor is going to be a squared, then the opposite sign, a times b, and then always a positive b squared at the end. This is a pattern that doesn't come up incredibly often, but when you catch it, it can make problems very, very easy. So if you can remember the process, I'm hesitant to tell students to memorize a lot of things, but this is something worth knowing, because when it does show up, it really can be very helpful. Factor by grouping. This only really works well for cubic functions. That's when it's especially trustworthy. But if we have 4 terms, which is usually indicative of a cubic function, then what we can do is, let's say we have ax cubed plus bx squared plus cx plus d. What we can do is group the first 2 and the last 2 terms in that function and find a greatest common factor from each. And then we have a distributive property that we can make work. And we'll see that illustrated more clearly in other examples. A common mistake students make is they try to factor by grouping when it just isn't possible. And we'll talk about that more in more detail when we get to examples that require it. And the second, or this final, the third technique, I just call it quadratic form. If a function follows the form of having a doubled up exponent, then just that exponent, and then a constant, then we can treat it as something to a second power and something to just that first power, that same something to the first power, and then a constant, and we can factor it just like a quadratic. We can use our magic numbers. We can use those techniques. All right, so our first couple examples factor the polynomial completely. The first thing we want to look for is a greatest common factor. All right, so we'll look for a GCF first here in number 6. I notice I can factor 4k cubed out of that expression, and I'm left with k squared minus 25. Now we're not done yet, because the factor that we have remaining, k squared minus 25, is a difference of squares. All right, so 4k cubed, that's still there. That doesn't go away. But then k plus 5, k minus 5. Now we cannot factor any of these further. That is factored completely. All right, number 10. Here I cannot factor out a coefficient, unfortunately, but I can factor out r to the 4th. Then I've got 3r squared minus 11r minus 20. And this r to the 4th, we don't have a difference of squares now, but we do have a trinomial. We should see if that factors further. If it does, then great. If not, then this would be our answer. So 3 times negative 20, negative 60, negative 15, and positive 4 are the magic numbers we're looking for. We'll divide by that a term on that trinomial, in this case a 3, and simplify. So I've got r to the 4th out front. Then I've got a r minus 5 factor and a 3r plus 4 factor. And again, that just comes from practice, knowing how to handle the trinomial solving techniques, or factoring techniques, I should say. All right, example 2. Here we've got y cubed and then 512. Well, let's just generate a little list of perfect cubes that we know. If I have 1 cubed, that's 1. 2 cubed is 8. 3 cubed, 27. 4 cubed, 64. 5 cubed, 125. 6 cubed, 6 times 6 times 6, is that 216? I believe it is. Let me get my calculator out here and just double check. Not a bad idea to have a list of perfect cubes that you've made just kind of on hand. 216, yep. Then 7 cubed, I think that's 343, yep. Then 8 cubed, is 512. Okay, so what we've got is really y cubed plus 8 cubed, and that's a sum of perfect cubes. So I take the cubed root of the first, keep the same sign, cubed root of the second, times the first thing, now it's squared. I want the opposite sign that I had in my other factor. First times second, that's 8y, and then plus the second thing squared. All right, and we should see if we can factor this trinomial further. Sometimes you might be able to, sometimes you won't. Y squared, or 1 and 64 is 64. What multiplies to get 64 and adds up to -8? Cannot do that with two numbers, so this is fully factored. Number 20, 135 z to the 8th can be taken out as a greatest common factor, leaving me with z cubed minus 8. And this is a difference of perfect cubes. 135z to the 8th, that's still a factor. It stays out front. And I've got the cubed root of the first, keep the same sign, cubed root of the second. And now I'm looking back to this original factor, that first thing squared. Opposite sign, first times second, and second thing squared. And again, if we were to try and factor this further, it is not possible, so this is fully factored. All right, number 28. Here, this is a good instance example of our factor by grouping method. So you'll see we've got 4 terms. It's a cubic function. Let's group these first 2 terms and second 2 terms together. And just remember that this is all hinging on undistributing. So what's the greatest common factor I can pull out of that first grouping? I can take z squared out of that, and I'm left with z minus 5. And ultimately, I want to be able to undistribute the quantity z minus 5. So here in this second grouping, it might not be the greatest common factor, but I want to see, can I factor something out of that grouping so that I'm left with another z minus 5? So I notice that if I can factor out a -9, then I'm left with z minus 5. And now we've got our binomials matching up. Now we can undistribute them, and this is what makes factor by grouping work. So I've got z minus 5 times z squared minus 9. All right, now it's not factored completely just yet. I notice that this z squared minus 9 is a difference of perfect squares. Z minus 5, z plus 3, z minus 3 is fully factored. For 36, I cannot take out a greatest common factor here, unfortunately, but we are lucky that, hey, 81 is a perfect square. A to the 4th, I can take the square root of that, right? That's just a squared squared. And then 256 is 16 squared. So if I factor that as a difference of squares, the square root of the first thing is 9a squared. Square root of the second thing is 16. So I've got plus 16, and then 9a squared minus 16. And this factor is a sum, so it cannot be factored further. However, this is a difference of perfect squares, so we can factor that further. Square root of the first is 3a. Square root of the second is 4. So we get factors of 3a plus 4 and 3a minus 4. And there we have it fully factored. Okay, example 4. Let's see, greatest common factor. I can take 4n squared out of everything. Then I'm left with n to the 10th minus 8n to the 5th plus 12. And I can think of that, it looks kind of like a trinomial. So this first thing is really n to the 5th squared minus 8 times that same n to the 5th plus 12. So I've got something squared and then something and then a constant. We can factor that like a regular trinomial. 4n squared, and then this will be n to the 5th. My magic numbers are minus 6 minus 2. And you can see that if we were to FOIL these back together, it was just as if this were x squared minus 8x plus 12. We factor that, except instead of x's, we had n to the 5th. So it's kind of a tricky thing to spot, but if we understand how the exponents are working and the pattern that they're following, then we can make that factoring work for us. This is a fully factored polynomial. All right, example 5, here we just need to determine if we have a factor or not. So number 40, we've got this long cubic function with big numbers, and the factor is x plus 7. Well, we could plug in a negative 7. So is the solution from this factor, negative 7, is that going to produce a function value of 0? Does it create that 0 product property that we saw up in the introduction? Well, with a cubic, plugging negative 7 into this would be really intense calculator work. We could do it, and that would be just fine. But it's also a really good opportunity to practice our synthetic division. Remember, if we run through synthetic, whatever our remainder is at the end is the same value as if we had plugged in a negative 7 all along. So I'm going to use that method because calculator is a sign of weakness. I like to try and do anything by hand as much as possible. So we drop down the 3, multiply by what's inside, add the column, multiply by what's inside, 343, add down the column, we get 372, multiply by what's inside. This is going to be a huge number, clearly not 0. So we know that x plus 7 is not a factor. So we don't even have to go all the way through that problem, to realize that that's just not going to work for us. Let's try 44. Again, another opportunity to try that same practice here. The solution would be negative 2. Let's run that through synthetic. 48x to the 4th. 36x cubed, negative 138x squared, negative 36x, and then we have 0 for a constant. You got to remember those placeholders. And let's see what our remainder ends up doing. Drop down the 48, multiply by what's inside, negative 96, negative 60, multiply by what's inside, we get positive 120. Add them up, we get a negative 18, multiply by what's inside, we get positive 36, so 0, multiply by what's inside, we get a 0, and hey, our remainder is 0. So x plus 2 is a factor. Always cool when we can tie multiple concepts together to solve a problem like this. And that does it. Really quick lesson today. This is the assignment for section 4.4.